All right, so good day, one and all. This is part 2 of the video on aromatic compound as taught by Professor Nkansa. This is being made by the GPSA Academic Board as a supplementary material, not an alternative material. Good. Now, last time we did some basic properties about aromatic compounds, and then we ended at reactions of aromatic compounds. Even though we've talked about aromatic compound reaction before, if I am supposed to remind us, I remind you that whilst talking about the properties, even though we are aware that in organic chemistry, there are two broad spectrum reactions that we can talk about, that is addition reaction and substitution reaction. We cancelled out the fact that aromatic compounds will not undergo addition reaction ultimately because it would destroy the extreme stability that they have, and no compound will want to go to a place where it becomes unstable, right? Good. So that was the argument that we put across. It means the reaction we are talking about here, we will limit ourselves to only substitution reaction. Very important. Now, in the substitution reaction, we have two broad spectrum reactions that we will still talk about. And then the first one that we'll focus on in this video is electrophilic aromatic reaction. There's another one, nucleophilic aromatic reaction, that we'll talk about later. Very important. Good. Now, before we can understand anything here, we have to understand an electrophile. An electrophile. I'm sure we are well abreast with substitution reaction already. So in substitution reaction, what happens is that one atom will go away and then a new one will be fixed. So if I have a carbon like this with 4 bonds around it, right? Good. Now, if let's say A is here, A is nothing, right? A is just an example. Good. If I'm talking about a substitution reaction, it means what will have to happen is that, assuming I want to bring B, I have to remove the A and then come and put the B here. That is what we call substitution reaction. Now, in this case, always what we remove is a hydrogen. So the net loss will be a loss of a hydrogen, and the net gain will be an addition of either a halogen, an alkyl group, an acyl group, a nitro group, sulfonic acid functional group, or a hydroxyl group. So that is what we are doing in this reaction, right? Good. Now let's talk about electrophile. Now, electrophile is actually a compound word from two different root words, electrons, philic. Good. Now, we know electrons already. Electrons are like this, negatively charged species, right? Good. Now, philic is love for, right? Affinity for. Good. And so this word means a species which has affinity for electrons, not electrons per se, but which has affinity for a negatively charged species. That is what we call electrophile, right? Good. Now let's think. Always, you realize that unlike poles attract. And so we are not wrong to assume, which is actually true, that if we are talking about an electrophile liking a negative charge, it means it should be positively charged, such that we will obey the general rule that unlike poles will attract. And that is true. Electrophiles are positively charged, right? Good. Now, what is the importance of that? It means if we are saying that electrophile is attacking the aromatic compound on the benzene ring, we are assuming that the benzene ring is negatively charged or is electron rich, which is true. The benzene ring has 3 pi bonds. Just the benzene has 3 pi bonds. Now, pi bonds are generally known to be very electron rich, right? Good. And so that is the means by which, or that is the ticket on which the electrophile can run on and attack the compound. So always, if you realize that when the attack is initiated, it is on the pi electron. Let's take note that what we are bringing in is a positively charged species. It has to be attracted by a negatively charged species. So the attack comes from the pi electron to the electrophile. Good. So that's the general introduction. Let's delve in. So this is a pictorial representation of substitution reaction. We have the benzene with a hydrogen, and then at the end it's being replaced by an alkyl group. an acyl group here, a halogen here, a sulfonal group here. This is a nitro group and hydroxyl group. Very simple. Good. Now, this is general mechanism for electrophilic aromatic substitution. Now, there's something very interesting that we'll talk about here. Very, very interesting. Good. Now, as we've said already, this is a symbol for electrophile E+, positively charged. Now, the attack will be initiated by the pi bond because it's electron rich, right? The arrow is moving always. The arrow moves from where the electron is traveling to where the electron is landing. So electrons are moving from the pi bond and then they are attacking the E. What happens here is that these electrons are being shared by this carbon and this carbon. Now, when the attack is initiated, this carbon will form a new bond with the E, with the E here. Now, when it forms a new bond with the E, it means this carbon no longer has the electron, so it becomes positively charged, right? So it's like it is losing the electron. The bond is breaking from this one, right? So it is loose, so it becomes positively charged. Now, this positively charged intermediate is highly unstable. It's highly unstable. And there's a little bit of stabilization that occurs because of delocalization of the cation here. We'll talk about the mechanism for that later. Good. Now, the next step in the reaction is that a base will come and take this hydrogen away as a proton, as H+. We've discussed how hydrogen leaves. In this time around, in this case, it's leaving as a proton, right? And then the electrons will break onto this. When it breaks onto this, right, it will restore the stability of the aromatic compound with a new substituent. That is the whole mechanism of the substitution reaction. Now, let's talk about some things that happen here. This first step here is the breaking of a double bond. Now, when a double bond is broken for a new substituent to come in, what we call it is addition reaction. And so it is very interesting to note that even though aromatic compounds will not undergo substitution reaction, in an attempt to undergo the substitution reaction, right, there's an addition reaction. They don't undergo addition reaction, They don't undergo addition reaction. But then when they are undergoing their substitution reaction, there is an addition reaction. That is the first step. Now, because the first step proceeds to form a very unstable product, right? Good. It is the slowest step, right? And then we call it the rate determinant step. Very simple. And this is a very fast step. So just two steps. The first one is the attack, that's the addition reaction. Next one is the base coming to take the hydrogen away, right? And then restoring of the pi bond system in the benzene ring. Very simple. Now, it is worthwhile to note that the benzene compound here is highly unreactive. And so before we can get it to react, we need a catalyst. Now, the catalyst that we use here is mostly a Lewis acid. For examples of the Lewis acid, we have aluminium chloride, we have iron chloride, we have ferrous bromide, right? This is ferric bromide, So ferric bromide, ferric. So iron 3, very simple. Good. Now let's talk about the intermediate. We said that it is very unstable. Now we are seeing that it is a little bit stabilized, right? It's a little bit stabilized by the delocalization of the cation. Now this is non-aromatic. Non-aromatic here because, this is even sp3. It is not aromatic. So the intermediate is not aromatic. It's not anti-aromatic. It is non-aromatic. We should take note of that, right? Good. Now, good. At the end of the day, what happens is that the cation will lose a proton, that is the H+ that goes away to restore the aromaticity. Good. Now, let's see how there is the delocalization of what? The cation. Now, upon the addition reaction, the first step, there's a cation form, right? Now, the electron, realizing that there's a cation form, would try and move. So this double bond will break onto this one, right? When it breaks onto it, there will be a new bond formed between this carbon and this carbon, and this one will lose the electron, so it will be positively charged. Then the next one, the next PC here, will break onto this. When it breaks onto this, there will be a new bond formed between this one and this one. And so what will happen is that this one will be positively charged, right? Good. Now, these are producing resonance structures. And this resonance structure will show how the positive charge, so this is the canonical structure, and this is the resonance hybrid. So showing how the positive charge is delocalized between the carbons, right? And that is a way of stabilizing the cation produced as an intermediate, right? Good, good. Now, we are saying that we should note that the mechanism of aromatic substitution involves two steps and an intermediate, which has been stabilized by resonance. So that is something that the reaction is always two steps, right? The first one being the rate determining step, the second one being the restoration of what? The aromaticity. Good. Now, we should also note that the intermediate form is what? Is stabilized by resonance. Good. Now, specific reactions. The first one, aromatic halogenation. By the name, you would realize that we are putting halogens on the benzene ring or the aromatic compound, right? Good. Now, what are the halogens we know? We know fluorine, we know chlorine, we know iodine, we know bromine, we know astatine, but the astatine doesn't react like these ones, so we put that away. Good. Now, you realize that among these, this is the most reactive and this is the least reactive. Now, these ones bring anomaly in the general reaction, right? Now, we are seeing that fluorine is highly reactive as we expect it to be. And so direct fluorination of aromatic ring leads to only poor yields of monofluorinated derivatives. Instead, electrophilic fluorinating reagents such as N-fluorobenzene sulfonamide and Selexfluor are used. So what we are seeing in the first long passage is that fluorine is highly reactive. And so when you use it in this reaction, it gives you a very low yield. So instead, use this. Now, I've seen this in exam before, trust me. This is how we do fluorination. We use these reagents, Selexfluor, and then NFSI. Very simple. Now, the chlorine and bromine are normal. I mean, their reactivity is manageable a little bit. And so what we have to do is that we have to just add the chlorine gas or the bromine liquid, right, in the presence of the benzene. And then we need a catalyst. If we are talking about chlorine, we'll use FeCl3. If you are talking about bromine, we'll use FeBr3 catalyst, right? And then that will give us the chloro or the bromobenzene that we want. Very simple. Very simple. Good. Now, we are saying iodine. We're expecting it to also bring a problem because it's the least reactive. If you are talking about iodine, we need an oxidizing agent. The one that we use usually is copper, right? Copper 2. So we can use copper 2, right? So we can use hydrogen peroxide as has been shown here, right? And we'll talk about how that one also occurs. Good. Before we can get our iodobenzene. Very simple. Good. So in the first step now, what is happening here? I'll just throw light on the reaction mechanism a little bit and then go out my way. So what is happening here is that if you can't understand the mechanism, just know that if you react or in the presence of the FeCl3, we'll get an electrophile out of the chlorine. The chlorine is Cl2 molecule on charge. But then for us to get the electrophile, which is the Cl plus from it, right, you have to get the lowest acid. Now, the property of lowest acid that is making it reactive is that they have empty orbital, so they can accept electrons. What happens here is that now this can accept electron to form another bond. So when it goes here and then it forms the new bond with it like this, this one becomes positively charged. When it becomes positively charged, the electrons here break onto this. It breaks onto this to stabilize the charge, right? That will give us the FeCl4 minus. And then this one, because the bond has been broken away, we get the Cl plus. Very simple. Good. Now, after producing our Cl plus, then the benzene, the pi electron of the benzene, to be very specific, will attack the Cl plus, right? Now, when it attacks it, we'll get the addition reaction here, very simple, right? And then this will be the base that will come and remove the H plus to form this byproduct, right? Come and remove this H plus to form, and then the bond between the hydrogen and the carbon here will break back to restore the positively charged here, the positive charge here. Very simple, right? A high yield process, 86% yield. Very simple. Good. Now, this is iodine. As we mentioned, iodine is very unreactive, so we need an oxidizing agent, right? Now, the one we employ here is copper 2. Copper 2. So this is a redox reaction occurring. Very simple reaction, right? If you have forgotten your redox reaction, you can just keep this in your head, even though it's very simple, right? So this is the redox reaction. Now, what have we gained from this reaction, or what have we gained by putting the oxidizing agent there? We have been able to generate an electrophile, a positive charge species from the iodine, right? Good. Now the next step will be that the pi electron here will attack this I plus, right? Will form our intermediate, and the base will come and remove the H plus here. And then the bond between the carbon and the H plus will break back to stabilize the aromaticity. Very simple. Very simple. Good. Now, we are not learning this reaction or this reaction because we like, but because they are very important. Take note of their significance. We are saying that chlorination is involved in the synthesis of diazepam. We are saying that in our body, right? In our body, we do iodation, right, of aromatic compound when we want to make thyroxine. So you realize that if you take the structure of these compounds, there's a chlorine moiety here, showing that there's chlorination along the line. There's iodine here, so that in our body, if you want to make thyroxine, that's in every living system. When they want to make thyroxine, they need what? Iodation. You need to undergo iodation. Very simple. The next thing, we are doing aromatic nitration. Aromatic nitration. Now, in order to produce the nitro group, we need two reagents. We need concentrated HNO3, and then we need H2SO4. This will help us produce our nitronium ion. Now, this nitronium ion will be the nitro substituent on the benzene. Good. So we have to look at how these two reagents will give us the nitronium ion. The nitronium ion. Good. Now, very simple. Let me just use this to explain everything here. So what has happened here? Now, this is the structure of H2SO4. H2SO4. Now, this is the structure. So what will happen here is that this one, the lone pair here will come and take the hydrogen. So take this hydrogen, right? Good. So the bond breaks onto this. Good. Now, when it takes the hydrogen, it will form a new bond with this hydrogen. So you have the O plus here. That means because it has formed more bonds, right? So if you look at this and then compare to this one, you realize that the only difference is that a new hydrogen has come here and there's a plus here. It's a plus here because it has donated this lone pair to a new compound. And then because people would also see that because oxygen has formed 3 bonds, right? It would have a plus. Always when oxygen forms 3 bonds, it has a plus. Very simple. Good. Now, this compound will have two positive charges, sorry, very unstable. So what will happen is that this bond will break onto this oxygen to stabilize. Is a negatively charged bond, right? So it will break onto this oxygen to stabilize the positive charge. Good. Then when that is happening, because this is going away, the negative oxygen here, right, the negative electrons on the oxygen would also be distributed or contributed to the nitrogen here. So there will be sharing between these two. There will be sharing between these two. And that will form your nitronium ion. Now, it is worth noting here is that whenever you have a group like this, H2O, this is like water, right? As a substituent on any compound, Now we see it is a good living group. So it can break off on its own, break off with the electrons, right? Good. So it's a good living group, put in your head. So always when you form this intermediate, it is a very good living group when it's a substituent. Very simple. Good. So I don't know if this is clear, but then it's quite, let me use a white screen to demonstrate what is happening here. White screen. So very simple. What we are saying is that we have now, I do the H2SO4 in a different way. On the other side, you can also draw it like this, OSO3H, and there's H here, right? Very simple. Good. Then we have good. So this was the other side, that's the HNO3. Now we are saying that the lone pairs here can attack this one, the hydrogen here, the bond breaks onto this. So we would have, now this one would be HSO 4 minus, right? This is the intermediate that we'll have. Very simple. That is from this one when we break one hydrogen. I mean, you should understand it's H2SO4. We have removed one hydrogen, so it will be HSO3 and HHO4 minus, right? Very simple. Now, from this one, what will form will be this. So the same O now bonding to two hydrogen atoms, right, with a positively charged and positive charge on it. Yes, minus plus. So this is what we'll have. Now the good living group will break off. So this bond will break onto this. Now this will break to restore the bond being broken. And so we would have water, right? When this one breaks off, it forms water plus our nitronium ion and double bond O plus. Very simple. Right. So this is the nitronium ion. Now the nitronium ion here will become our electrophile. So if I'm supposed to continue, it's very simple. The same thing that the benzene ring, the electrons, right? The pi electron will attack it. So the same old story. The pi bond will attack it, and then we'll go on and on and on like that. Let's use a slide to explain that part. Right. So what will happen here is that the pi electrons, now this bond is moving from the pi electron, right, to the nitrogen, which is positively charged. Now this bond will break because a new bond is being formed. This bond will break, right, break onto the oxygen to become negatively charged here. Then a base in the medium. Now in this case, the base here is water. So come and take the hydrogen away, and then bond will break to stabilize this. Very simple. So the bond between the carbon and hydrogen will break, stabilize the positive charge to get your final product. Very simple. Very, very simple. So this is nitration. Now we are saying that note that nitration does not necessarily occur in nature, right? But what happens is that if you want to form aniline, we first have to form a nitro, right? That's we have to form nitrobenzene, and then we reduce our nitrobenzene to aniline. Very simple. Good. Now, aromatic sulfonation. Good. So the first thing we have to do always is that we have to generate our electrophile. How would we generate our electrophile? We are saying that this electrophile is generated by autoprotonation. So what you have here is that you have the same molecule, two equal molecules of H2SO4. But one is protonating the other. That is what we call autoprotonation, right? Autoprotonation. So the lone pairs here would be donated to this one. So it's like the electron here is going to take this proton away. Take the H plus here, the bond will break onto this oxygen. So you form these intermediates. The byproduct from this one, let me show a pointer. So yeah, that's what you have here. Now the byproduct of this one is this. I mean, it's H2SO4. If you remove one hydrogen from it, so you have HSO4 minus, right? Now, after taking the hydrogen here, you would have a positive charge, right, on this because the lone pairs have been donated, right? to a different compound. So oxygen is forming 3 bonds here, positive charge. Now, as I said, OH2 or H2 is a very good living group. So whenever it's substituted, it will live on its own. A very good living group. The living groups that we have N2, H2 like this. We have the halogens too are very good living groups, right? Good living groups. We will discover more with time. Now, so it would live on its own. When it leaves like this, its leaving is the bond breaking onto the oxygen to stabilize the positive charge. So we'll have the byproduct water being also formed, right? Now, when this one is breaking, the lone pair on this oxygen is also being donated to restore the number of bonds around the sulfur. So you realize that this one is being broken, and then at the same time, the lone pairs here are being donated to the sulfur here. Very simple, right? So you come and form this intermediate. Good. Now, from this intermediate, what are we looking at? We are looking at this bond breaking onto the oxygen. Or when it breaks to stabilize the oxygen here, right? You come and get this. Why are we getting that? When the bond breaks onto this, it means the sulfur is losing electrons, so it will become positively charged, right? It will become positively charged. Now, the positive charge here, because electrons are broken onto it, will also be neutralized. So you have this. Now, this is the electrophile we are interested in. But then, because of the side products there, there's an equilibrium reaction, reversible reaction between the electrophile we are interested in and this product, right? Because of this, usually what happens is that this can attract one proton so that I can form the sulfuric acid back and then get this. Or this can also take a proton from here, form the electrophile we are interested in, and then this byproduct. So there's an equilibrium reaction between these two, right? After forming this intermediate. Very simple. Very simple. Now, after forming our electrophile, the next one is to show how the attack occurs. Good. So the same old story. So what will happen is that the pi bond here will attack the sulfur because it's positively charged, right? Now, when the attack, this bond will break. One of the bonds will break because a new bond is being formed. One of the bonds will break. So you realize that at this point you have O minus because one of the bonds broke. There's no arrow to show that. So one of these bonds will break. So we would have something like this, right? So then next step is the base coming in. The base here can be this. It can be SO4. You should understand this because you realize your conjugate acid base pair. That should make sense to you that once you have the acid donating its proton, it becomes a conjugate base, right? Good. So come and take a proton. You can come and take a proton. From here. Or it can also be water in the medium. That's the H2, right? Can come and take a proton. When it takes the proton, then the bond between the carbon and proton will break back to stabilize this. So this is our sulfonyl functional, right? Now, we are talking about importance of aromatic sulfonation. Even though it doesn't occur in nature, we can use it to make some dyes and pharmaceuticals like sulfanilamide, right? So if you want to synthesize sulfanilamide, we need to do sulfonation reaction. Very important. Next. So next up, we are talking about aromatic hydroxylation, right? Now, it is very easy for us to talk about aromatic hydroxylation in forming diazonium salts. And so instead of talking about it here, we just mentioned it. There's no explanation. When you get to the diazonium salt, we'll show you how phenols are formed, right? That's how hydroxylation is done. Very simple. Now we have a question here that we have to try our hands on. The question says that we have to write down the chemical structure for cyclopentatrienal cation, cyclopentatrienal radical, cyclopentatrienal anion, and explain which of the structures are aromatic. So we've done something around this in the previous video. Yes, but let's try this. You realize that there's some mix up in the question. Yes, because these ones, none of them will really be aromatic. None of them will be aromatic. None of them. So the actual question And this one was intentionally placed there, I mean, from the information I gather. So it's either we are talking about cyclopentadienyl or cycloheptatriene. And I think the information I gather ideally was supposed to be cyclohepta, right? So we'll use that to solve the question, cyclohepta, and then we'll show which of them. Let's share a white screen and talk about that. Good. So, so this is cycloheptene. I mean, my lines are no lines. 1, 2, 3, 4, 5. Oh God. This is not nice. Let me change it. Let me change it. Okay. So straight lines. So 1. Oh God. Oh. Oh. I mean, I think I have to use my eyes to draw it. So I have to use my eyes. Okay, so back to business and change the ink. Okay. 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 Wow. Okay. So forgive my horrible drawing. So this is it for, so this is the normal compound, right? Now this is how the cation will look like. This doesn't look nice, but bear with me. Good. So this is the cation. I mean, this one has 2 hydrogens, the normal compound. So this is the cation when we have lost 1 hydrogen. Now that hydrogen went as a hydride. Very important. We've talked about all those already. This is not nice. Right. So this one right here. This one right here will be the radical. The last one I'm drawing. Wow. So hydrogen. This one right here can be the anion. Very simple. But these structures are not nice. Good. So this is a normal compound. A normal compound is not aromatic, right? This is cycloheptatriene. It is not aromatic because this carbon here is sp3, so it would cancel it out, right? It's sp3. All carbons in aromatic compounds should be sp2, right? So this is not aromatic. Now it is also not aromatic. Okay, so here let's talk about this one. Now, when you lose the hydrogen, right? What happens here is that the hybridization here will change to sp2. So all of these will have sp2. I mean, in terms of the hybridization, they are in terms of the hybridization of the carbons, they have passed, right? Good, but there are other criteria. So here it was obeying the Haeckel's rule. It had 6 pi electrons, right? Good, but it wasn't obeying this. Now in this instance, we have lost this, right? 1 proton from here. It's now sp2. Now it obeys the Haeckel's rule. So this can be said to be aromatic. So this is aromatic, right? Good. Now, if on the loss of the hydrogen here as a hydrogen radical, you realize that this is sp2, but then we have 6 pi electron here, plus the radical, which will also be contributed here. And so we would have 7 pi electrons. Now, the 7 pi electrons here cannot make it aromatic. So this is not aromatic, right? Now, the last one here, we have the hydrogen going away as a proton. So we have this, right? Now the hybridization is sp2, all right. But then these electrons will be contributed to the pi system. So we would have 8 pi electrons. Now, once it's having 8 pi electrons, It doesn't obey the Hackles rule. So this one is not also aromatic. So very simple. The one which will be aromatic will be the cation. The cation. Very simple. Very simple. So let's go back to our discussion. Good. Now, a new field for us to explore. Aromatic alkylation and acylation reactions. So we are saying that aromatic alkylation, synthesis of aromatic hydrocarbons, can be achieved through these three ways. So if you want to form aromatic hydrocarbons, it's either you are doing Friedel-Crafts alkylation, Clemenson's reduction, or Wurtz-Fittings reaction. We'll talk about all these. Good. The next one, we have Friedel-Crafts acylation, right? So okay, we are talking about alkylation. Let's finish alkylation. We'll talk about the acylation too. Good. So in the alkylation reaction, what we need is the aromatic compound like the benzene ring, right? Good. Now we also need an alkyl halide, right? The common one that we use is an alkyl chloride. And so because of a lot of negations and all, for Friedel-Crafts, we have limited ourselves to alkyl chlorides, right? Now we use the alkyl chloride in the presence of an obvious catalyst, which is AlCO3. That's the lowest acid catalyst, right? Good. Now, what happens is that, as has been illustrated in the Hexane example, the lowest acid will help us generate an electrophile. It will help us generate an electrophile, right? And then the electrophile will be attacked by the benzene ring. Very simple. Good. Good. So that is what will happen here. If I'm supposed to show the mechanism, what happens here is that the lone pairs here can attack this aluminium because it has empty orbital, right? Now, when the attack is formed and the bond is formed between this and this one becomes positively charged, right? Then this bond will break onto the chlorine. So the next thing that will happen is that the chlorine here will be here as negatively species because it has broken this electron off. And then there will be what? There will be an electrophile generated out of the alkyl chain, right? Good. Very simple. Now, there's something worth noting here that we'll talk about subsequently, is that always when the cation is formed, the compound will ask itself. The compound here, it will ask itself, is this my most stable state? Is this my most stable state? So assuming the compound is a primary cation, right? And then it can go to a secondary carbocation. It will move and it will change its position towards secondary. If it is secondary and it can shift by moving just one atom, right, to form tertiary, then it will shift and form that tertiary. Are we following that discussion? So always there's something that we call an alkyl shift or a hydride shift. And these shifts are to form a more stable carbocation. So there's rearrangement to form a more stable carbocation. So always when you are doing this reaction and you get here, you have to ask the compound, or you have to ask yourself that, can I form a more stable carbocation by moving just one atom? Very simple. Good. Now this one we will not change anything because it's secondary, right? If I move the plus sign to this one, it becomes primary. If I move it here, it becomes primary. I mean, no carbon would want to go to an unstable state because the primary is least stable, right? So it will maintain this. Now, after maintaining that, what will happen is that the same thing that we know, there will be the addition reaction, and then subsequently, this one will come and take the hydrogen for it to restore the aromaticity. So the same reaction step occur. Very simple. Now, there are limitations of this as Friedel-Crafts alkylation reaction. So the first one is that only alkyl halides can be used, right? If we have aryl halides and vinylic halides, they will show no visible reaction. I have seen questions where we would have benzene ring, right? So there will be a benzene ring like this. So benzene ring like this, reacting with this in the presence of maybe AlCl3. If you have not read this limitation, you would think it's Friedel-Crafts alkylation, so you would react to them. No, we are saying that these ones will not show any visible reaction. So if you see this, and then these conditions, it will not show any visible reaction. Pay attention to this. Good. Next up. Good. Now we are seeing there's no feasible reaction with aromatic rings already having electron withdrawing substituents or amino groups. So if we have benzene with an amino group, right? Good. Whether it's primary, secondary, or tertiary, right? Good. Or if you have any of these species, any electron withdrawing group, take note of these species, right? If you have any of these electron withdrawing, we'll talk about these groups further. Any of these electron withdrawing groups, you will not have any feasible reaction. Very important. So if I give you aniline plus maybe methyl chloride, right? Plus methyl chloride in the presence of ELCl, you are not getting anything. Very important. Take note of this. Next one, it is difficult to control polyalkylation. So sometimes your aim is monoalkylation, that you want to do this so that you can just get one of this, just this. But then you realize that the alkylation can occur in just more than one position. So what some will not happen at all, some will be mono, some will be bi. So polyalkylation is difficult to control, right? Now the last one is what I was talking about, that always there's skeletal rearrangement to form a more stable carbocation. So after the carbocation has been formed by the lowest acid, right? Good. The next thing is that there will be rearrangement. Now that rearrangement can make you form an undesired product because the compound is rearranging itself, right, to form a new compound. Now, ideally, you wanted to put in something. What will happen is that what you wanted to put in might not be what is happening. So this is also a limitation, that there's always skeletal rearrangement of the alkyl electrophile to form a more stable carbocation. Very important. Very important. So an example is what they have illustrated here. We'll do one so that we can also see, but let's follow what has happened here. So you realize that